Question 2. We're going to do the exact same thing that we did with question 1. We're going to draw a force diagram. We're going to look at the forces in X, look at the forces in Y, write down the friction equation, and then see where we're at. I haven't even studied the question to see what in particular it's asking me to calculate because it doesn't matter. My process is always the same. I always do these steps. In this case, I have a car traveling along a highway and it is attempting to stop. And so the forces involved are going to be between the car and the road. So here's a representative wheel for the car, and let's say it is traveling in the forward direction from left to right, which means that as it's trying to stop, the force acting on my car is going to be to the left. That is my friction force. And there will be a downward force, which will be the weight of the car, and there will be an upward force, which is the normal force represented by that upward arrow. So I've got normal there, I've got mg there. That's it. There are no other forces acting on the car. Do not feel like you always have to have a force acting in each and every direction. That is not the case. The forces that we put on a diagram are just the forces that are applicable for our individual situation. That's a common mistake that people make. They feel like they need to always put a forward force and a backward force. This is a car slowing down. You're not going to be hitting the brakes to slow down and keeping your foot on the gas, trying to make the car go forward at the same time. So what we're being asked to find is the stopping distance of the car, and we're nowhere near being able to do that. So let's just follow our process and see where it leads us to. So we'll start with looking at our forces in Y. And the car is not accelerating in Y, because to accelerate in Y, the car would have to be speeding up by rising into the air or speeding up by sinking down into the road. And it's not doing either of those things. So in purely vertical motion, the car is not accelerating. Net force in Y equals 0. Same process as we followed many times. We add up those forces. We've got a positive N and a negative mg. So 0 equals N minus mg, and N is equal to mg. That's becoming a bit repetitive, isn't it? We've found that several times now. Do not assume that N will always be equal to mg. It will not be the case every single time. It's quite common, but it is not universal. We have to figure that out every time. Let's look at the forces in X this time. Now, this car is slowing down, so it is accelerating. I cannot say net force is 0. I have to say net force is equal to mg. Sorry, ma. The net force acting on this particular car, well, there's only one. It's to the left, so negative, and it's the friction force, F. I put these two lines together to give me that MA must be equal to negative F. That gives me a second equation. And the last thing that I get is the friction equation, right? That F is equal to mu K times N. Sorry, mu times N. We're not being specific as to which type of friction we're dealing with, but in this case, it would be rolling friction, which is a variant of static friction. It's not totally relevant to the question, so we'll just leave it non-specific. Okay, I've got 3 equations, and I'll see what I can do with those. What is the problem asking me to do? It says, if the coefficient is a certain value, given up here, then what is the minimum distance in which the car will stop? So we're looking for a delta x value, and the question has also given us some information about the speed of the car, so that's a velocity. Now, delta x, displacement, and velocity, those are motion related, and everything we've done so far is forces related. So we've got to somehow bridge those two worlds, the world of forces and the world of motion. And I'm hoping you all remember that if we need to bridge the two worlds, it's always via acceleration. Right? Acceleration will lead you from forces into motion or from motion into forces. And if we look at the information that we've developed so far, we can see there is an acceleration term in one of our three equations. So perhaps if we can find that acceleration, it will lead us forward. But let's just confirm that. I'm going to do the standard approach to a motion problem, which is I start off, if there is acceleration, by listing the 5 possible variables that I might know about the situation. And I'm going to fill in the ones that I'm given, right? I'm told the car is traveling at 51 kilometers per hour. So that is how fast it is traveling. That is my initial velocity. The car is going to slow down and stop, so its final velocity is going to be 0. And what I'd like to find is how far it goes whilst it's stopping. What is the delta x for the car? I cannot solve this just yet, because in order to fill in any missing variables, I need to know 3 of the other ones. And I know 2 of the others. I do not have a third. I cannot solve for delta x without knowing either the value of a or the value of t. And I'm not given a or t in the problem, so this is impossible and we should just give up and go home. Or, alternatively, we could say, hold on a minute, we just did all of this work in forces, and we know that the bridge between forces and acceleration, forces and motion is always acceleration. So can we use the information that we got about forces to find the acceleration, right? Can we find this acceleration here and plug it in over there in order to then give us our third variable? Well, let's see. If I want to solve for the acceleration, I would need to know the mass of the car. And gosh, I don't seem to be given that. And I would also need to know the size of the frictional force on the car. And I don't seem to be given that either. So does that mean that the whole problem is impossible? Well, in forces problems, if we have an unknown variable, there's 2 things that can happen. One, we might be able to substitute for it, replace it with something that we do know. Or 2, if we just do a little bit of mathy algebra, we might find that the unknown variable will disappear from our equation. It might cancel out. So let's see what we can do. Let's start by saying I can replace this f with mu times n, because I know that they are equal to each other. So wherever there's an f, I can write mu n instead. So if I take this equation here, I can write it as m times a equals minus mu times n. That's partly solved my problem, but I still don't know the mass of the car. And although the problem does tell me what the coefficient is, it's given right here. That's my value of mu. I can say, yeah, I know that. I do not know what the normal force of the car is. What else could we do? Well, I've got another equation over here I haven't looked at yet. And this equation tells me that the normal force is the same as mg. So instead of writing n for normal force, I can write mg for mass times the acceleration due to gravity. So let's do that. That would give me m times a equals negative mu times m times g. And I'm hoping this jumps out at you, but at this point, see how we've got the m on both sides? It can just cancel out. that is going to give me an equation that says acceleration is minus mu g. And I know both of those things. Mu is given in the question. G is just a number. It's 9.8 meters per second squared. So I can plug those in and say that my acceleration is going to be minus 0.102 times 9.8. 0.102 times 9.8. And once you've worked that out, it will give you the acceleration in meters per second squared, which we can plug in over here to give us the acceleration that we need in order to solve for delta x. How do we solve for that delta x? Well, this is standard kinematics. We've done a million of these. I do not know the time, so I'm looking for whichever kinematic equation does not have time in it. So I'm going to start with Vf squared equals Vi squared plus 2a delta x. I need to rearrange that so it says delta x equals, and that rearrangement would be Vf squared minus Vi squared divided by 2 times the acceleration. This is why it's important that we ended up with this negative sign up here in our acceleration, because on the top row of the equation that we've just derived, right, it's Vf minus Vi, and so we're going to have 0 subtract our initial velocity squared. So we're going to have a negative on the top row, but because we've got a negative acceleration, we're also going to have a negative on the bottom row, and we're going to end up with a positive displacement, which is the only thing that makes sense. One final thing that we need to bear in mind, and that is that we have been given a velocity in kilometers per hour. And when we're doing these motion problems, we need to make sure that we have all of our values in meters per second and not in kilometers per hour. So here's a very quick review of how we would turn those kilometers per hour into meters per second. So I've got 51 kilometers per hour. That's kilometers divided by hours. I know that 1,000 meters is the same as 1 kilometer. And I know that 1 hour is the same as 3,600 seconds. If I multiply by those ratios, my kilometers will cancel, my hours will cancel, and that will leave me with meters divided by seconds, meters per second. That's what I wanted. So that is the correct way of multiplying by the ratios. That will give me an answer for my initial velocity in meters per second, which I can then plug in to my equation that I already developed. I get the acceleration from my work on forces. I get my velocity initial in meters per second. My velocity final is 0 because I'm stopping the car. Everything else is just put those numbers in your calculator and find the answer.